So California Resource Board deemed that you don't need a refinery. Because if you're operating a refinery the way it's supposed to be operated, why would you need a refinery? And they're serious. Yeah. And you're like, yeah, okay.
You start recording whenever it's time.
I'm starting right now. I was thinking that when, yeah, they're just gonna shop in, so I'll take that. I'll put my head in a couple minutes, make everything's so good.
And we're good.
Good turnout for your meeting this morning.
Yeah, I mean, yeah, considered it's early and, you know, there's 20 or so people in there. And so had almost as many people at the end as I did in the beginning, so. Didn't run everybody off.
Sure, they do that opt-out thing.
Yeah. Some such. I was excited. All right. Y'all doing okay today?
Yeah.
Very good. I've been attending trainings this morning. Feel educated.
I know.
That's it.
I started this morning.
See a couple familiar faces from this morning. We'll give it a few more minutes or in case some people are. So who all went to another presentation that was canceled so far today? I think I actually sent you to a second one that was canceled. I sent somebody else and they're like, yeah, we already went there and they're not here today.
Clear problems are together.
I mean, we're separate. We entered into a minority share investment in them in 2019 with focusing on the technology around optical gas imaging that they're making.
So does their technology only support clear now or?
Correct. Well, they have three pillars. They have technology that supports us with this Thomas Leak and quantification, but their Mantis is not directly related to FLIR technology at this time. For their combustion efficiency for FLIRs. They've been doing a lot of engineering work on that as well. Howdy. They don't make these doors easy to sneak in, do they?
I tried.
Give another 2 minutes and then. Oh, I didn't update that. Oops. So how many of y'all use infrared, use optical gas imaging? Handful? Does anybody have ventured into the continuous autonomous fixed mount OGI world yet? Okay, just curious. And of course, everybody has a FLIR, right? Not biased. Well, in essence of time, I'll go ahead and get started with everybody here. Well, I appreciate y'all joining us, or joining myself, my partner, Providence Photonics. John Morris is one. He got called away. He's actually in Norway right now, who is the CTO for Providence. But Yoshing Zing may pop his head in. He's the CEO, and realistically, the two of them are the brains behind the autonomous leak detection technologies. Those of you that don't know me, my name is Craig O'Neill. I am with FLIR, and I've been with FLIR for almost 20 years. And in that time, I have been directly involved in optical gas imaging since the inception of OGI in 2005, when we came out with the first commercial OGI camera. Seen a lot of changes over the years and what happens. One of our leading partners over that tenure is Providence Photonics. Providence, when we first came out with a gas find IR, Yoshing and his team looked at it and said, yeah, this is going to be our life too. They really dedicated a fair amount of assets, brain power, and everything to advancing the optical gas imaging technology in really unique ways. And their first foray into it was the autonomous leak detection solution, which we'll talk a little bit. So a lot of what we're doing here within Teledyne FLIR is in conjunction with the engineering efforts. In essence, I kind of say that the Providence team is kind of our engineering on optical gas imaging in the States, and realistically our engineering focusing on continuous monitoring, autonomous leak detection, as well as our quantification solution, which shameless plug, we'll have another one of these presentations tomorrow at the same time next door. So so we'll be able to talk a little bit more about some advancements in the QOGI technology. But before we get into kind of what some of the advancements that we're making in our complete autonomous solution, I wanted to kind of take that walk down history lane and talk a little bit about where OGI, where it started as it relates to an ALD or autonomous leak detection solution with the Providence team. It was around 2005 when they first reached out to us. They actually had the gas find IR originally and looking at that, but we didn't have a fixed mount solution at the time when they began working with us. And in 2009, the Providence team came out in 2009 and took our handheld camera, took some of the stuff off of it. They re-engineered our GF320, at the time it was a GF300 camera, and made it, and the whole design and goal for making an autonomous leak detection solution. As you can imagine, when your starting base point is a $100,000 camera, and then you start adding stuff to it, it was quite the advanced and expensive solution and technology that we've looked to try to advance recently, as well as move forward. And so what they're utilizing was, in essence, the output videos you can see on this. You've got, you know, the back end of this, and you've got the processor electronics to make it run longer. But in essence, just utilizing the core handheld camera as that technology. Simple goal was to have an autonomous or a continuous monitoring type of solution to do that. The next phase that we moved into after, after the Providence team utilized a handheld solution for a fixed mount problem, was in 2014. And what we did there is we put the cooled optical gas imaging technology. In essence, you take the engine of our car and put it in a different chassis with different needs. So that's where we engineered the G300A, which is still in the market today. It is nothing more than the GF300 or the GF320 camera. All the insides of the detector, the filter, all those insides put into a box that just sits there with some back-end electronics to try to make it a little bit more streamlined in how it works. Had an Ethernet back-end interface, and we provide a software development kit for integrators and those, people like Providence that want to try to make this be able to be used. They developed, in partnership with a large oil and gas company, they developed the first optical gas imaging autonomous leak detection software, an analytic, if you will. And it was called IntelliRed, which is still it's still on their website, and it's still a piece. But they're far and away they were real pioneers in the autonomous leak detection analytics. And then they put that with a multi-focus lens. You can see this huge lens right here on the front of this, which is, if you've ever seen an OGI camera from FLIR, you don't see lenses like that. So they had a specially engineered lens for this application. You're also going to have a visual camera and install it kind of, realistically, put it in a box and let it sit out there and stare. As you can imagine, it was not the most inexpensive solution at the time, and still isn't. But there were customers that were pioneers in the utilization of this. They were able to get, by using the 300A versus the handheld unit, able to really kind of come down and streamline the price, the MSRP on it. But the challenge, and still is somewhat of a challenge today, is the price as it relates to upstream applications of the camera system. It's still, the technology is still, we're trying to work with customers around that. We can look at, like a hardware as a service model to try to hit a different, try to get away from a CapEx expense if that's necessary to streamline that out. But the reality is optical gas imaging, in particular, the cooled optical gas imaging technology, it's not inexpensive to manufacture and to develop and put out. Initially, a lot of these, are not initially, a lot of this was more pipeline, refinery type. More recently, if you look at, any type of Associated Press or whatever, they don't talk about anything but methane. And so the goal, the industry's changing a little bit with regards to focus for autonomous leak detection. It's not as broad hydrocarbon based. There's a number of reasons. The methane technology, which again is a little bit different than that. But if we're to look down kind of a little bit at some of one operator in particular that was a pioneer in autonomous leak detection, utilizing a continuous monitoring solution, or at least a fixed mount solution for a unique application. There's a quick video from BP back in, I think this is around the 2010, 2011 timeframe, I believe, from their marketing website.
BP uses FLIR cameras, a new thermal imaging technology to inspect difficult-to-reach pipelines leaks and detect leaks before humans can see them. Because safety is never being satisfied and always working to.
So while that wasn't like a continuous fixed mount monitoring, it's really very similar in how it works. It's hard to walk around. To inspect pipelines, very challenging to do. In Alaska, it adds a new a new challenge with handheld type of use. But realistically, it is very similar in what they're trying to do, except for it's just not fixed mount. Oh, I really like that video. I want to show you again. What they're trying to do, it's just trying to find a better way to inspect a vast land of pipelines and utilize it. Very similar to if you were to put a continuous monitoring with a pan and tilt. As I mentioned, one of the big changes, or some of the big changes, in technology, as well as where the industry is focusing on, is really focusing on that word methane outside. A lot of the technologies for methane can be a little bit more streamlined and less more cost sensitive to an operator, to an end user. And one of those is uncooled optical gas imaging. What you're able to do with an uncooled camera and a lot of these methane centric technologies you're able to utilize a long wave camera that doesn't have that cooler in it. So, when you turn on a FLIR camera and you hear what I love is the most beautiful sound you ever hear, is that big hum. What that is a cooler operating, getting the camera down to negative 321 degrees Fahrenheit, stabilizing at a cryogenic base. That's why it takes 7-8 minutes and do that. Well, that's just an extra operation, all this. Those cameras are super, super sensitive. To be able to get a cool camera down, to have that type of image, that quality, is why they're Quantification approved and Quantification compliant. Well, the industry is kind of looking elsewhere, and one of those is our uncooled long wave camera. This is actually the fixed mount version of our GF77 that we're giving away at the Reverbery tonight in the handheld solution. So all we're doing is taking the same handheld solution that we've had out for a couple of years, ripping everything out and putting it into a fixed mount sensor, uncooled. The big difference, what you're going to get it's a fully radiometrically calibrated. It's got an integrated right here. You got visible cameras. There's your thermal camera. We filter the camera on the back of the lens. So we have, the filtering is done for methane methane's around a 7.7 micron absorption spectrum in long wave. So we can filter this from 7 to 8.5 and be able to focus on methane and some other similar gases. The back end is going to be GIGI, RTSP, ONVIF compliant. So really meets a lot of those protocols. But what you are going to potentially miss with this is the sensitivity. An uncooled camera is not going to give you what you're used to. If you're an OGI guy and you've been doing OGI for years, or any time and you've used a cooled camera and you grab this, you're going to be underwhelmed. It's the guy that never eaten anything but filet mignon. Somebody gives him a skirt steak and says, "Hey, it's pretty good." Yeah, it's probably pretty good, but if all I've eaten is filet, it may not be, it may not meet my standards. So the uncooled solution is about 5 to 10 times in ideal conditions. It's about 5 to 10 times for pure methane less sensitive than the cooled counterpart. So what's going to happen is you're going to that threshold for what the problem that this camera is going to solve is different. This is not going to be a fixed mount continuous solution to solve Quantification compliancy. This is going to be a fixed mount continuous solution to lead that next generation of methane detection solutions. Yeah.
I heard you say, how wide is the window? You said around 7.5.
It's 7 to 8.5. It's a 1.5 micron window. 7.7 methane pretty much peaks down and back up in the long wave. 7.7. It's like, it's 7.7 plus or minus like 2.
What interferences do you have in that segment? But it's real thin. Resides water.
That's the biggest interference you're going to have. That's one reason a lot of infrared imagers, long wave infrared imagers, like a handheld for temperature measurement, they cut it off at 8 because there is a water absorption interference in that. But in the applications that another gas that falls into that range is sulfur dioxide. So it's a pretty big industrial gas. We've had some need. There's also laughing gas, nitrous oxide is one. Reality is where you're going to mount this, where you put it. Methane's going to be the only thing it really sees in respect to that. Correct. Yeah. And so, this is, again, it's going to change as the industry looks for methane mitigation technologies. This is this is part of that next generation envelope. But what optical gas imaging gives you, what OGI gives you with whether it's this, again, if you're going to change that goalpost, if we really want to look at those bigger leaks, the super emitter type of stuff, what optical gas imaging is going to give you is the opportunity to have situational awareness of what's happening. If I see a leak with this sensor or any type of detection technology that just says leak or no leak, is it a vent or is it a leak? And it is what's happening. There are scenarios that you don't want to happen, but a lot of them are allowable especially in the upstream where methane mitigation technologies might fall. So this gives you capability to store a quick video, look at it and say, yeah, I see what's going on there. That Inardo valve did its job and it's not doing it anymore. Whereas a lot of other technologies like beep, oh, we've got methane, we've got to get out there. Something happened and we don't understand the situational awareness of what's happening on site.
In the world of we have an analysis for the midway rule
Mhm.
of grams per hour that we've always used for
Correct.
2005.
Yep.
Do you have a number for this?
Yeah. So 2005, the grams per hour, you're looking at around 0.6. I think 0.8 was our very first one. 0.6, we've done testing that is way below 0.6. We're not going to put that into public writing for a number of reasons as far as our minimum detectable grams per hour rate of our cooled system. But 0.6 is a very good baseline for the cooled system. The uncooled system for methane is going to be about 5x in the grams in a minimum detectable leak rate in laboratory controlled environments. Keep in mind, this is pure methane. So you're looking at about a 5x or so difference. Let's take a 5 to 10x change. It's 2.7 in really controlled testing environments through the National Physical Laboratory in the UK. So we're looking at about a 5x difference in that, but that's pure methane. Yes.
3 grams an hour?
Yep. Yeah. Of methane. Yes. So now when you look at getting into the industry, the reason it's not quad away is not pure methane. It's half propane. There's a reason it's half propane. It dilutes it and makes a lot of the methane mitigation, these sole methane mitigation technologies that are more challenging to be able to utilize for propane, that propane side of the detection. But but you're looking at about 5 now. If you look at the U.S. shale average, is approximately 70% methane. You got 2/3 ethane, 1/3 propane, realistically, and then some other gas at the end. So now you take that, let's say 5% or 5x. Now you add another 30% of air on top, of less sensitivity on top of that. You're probably talking, 7 to 10% change in minimum detectability as far as minimum sensitivity standards go for that. Yeah. And I have some stuff in here to kind of talk about. Yeah. What we have worked with Providence in the last year is the development of a complete autonomous solution. It's going to have that 77A inside, and it's going to have the smarts of the Providence team and the analytics that are going to be built into a small computer that would be inside that controller or mounted very near it. Pan and tilt. This is just a FLIR pan and tilt system with a D100 pan and tilt, full edge detection with the Providence analytic. ONVIF compliant. They do have quantification that they're looking at enabling on that full remote control as well as communication. So you can send a video, you can send 20 seconds. You can have it always record and send a previous 10 and post 10, right? It has an alarm. The alarm has to hold for 10 seconds or whatever that is. You could send previous 10 and post 10 seconds before the alarm got there to kind of see what's happening. This is methane selective, but low cost. We're still allowing or figuring out where we're going to put, but a full-on solution like this for a cooled solution is going to be in the near $100,000. Where we would expect this to be half that or lower in as far as a marketable type of price point for that. And again, because it is methane centric, it's geared more for that upstream, midstream natural gas operations for the most part. To kind of give you some examples of what we've done, we've spent some time out at the METEC facility and evaluated the technology for various applications. This is just one where it's highlighting the leak. in the standard Providence Photonics colorized plume scenario, where this is, I don't remember the numbers. I have the numbers of these leaks somewhere, but this is at around 4 meters away. Doing this is probably not the ideal distance that you would probably normally have, but we spent 3 days at METEC full and doing nothing but recording, and we had 4 cameras, 4 operators, and 2 cameras were in a man lift recording 24, almost for all 8 hours of the day. 2 cameras were on the ground recording all of this stuff with both cooled and uncooled technology to try to help help advance our autonomous leak detection solution, as well as the analytics that the Providence team would be looking at putting together. Just another example of this. What's unique about this is with our more narrow field of view lens, but you're also looking at a 60-meter distance for something like this. This is going to be, I don't remember. I know that the maximum leak rate that METEC would allow at that time was, I believe, 90 liters per minute. This may be somewhere in that range for if you're looking at an estimated size of what this could do. But again, we're not saying it will, and we're not marketing this as a quad OA 60 gram per hour type of leak. This is going to be going to be something that would solve that different need of the market. Is that industry requirement regulation, or is it ESG, right? Is our organization looking to say, you know what, Vanguard Financial is not going to put us in their portfolio unless we do something like this? And this is where, when the operators, people like yourself, want to look at moving down that road, we just want to make sure everybody knows that FLIR and Providence and the optical gas imaging technology, when those goalposts move, we're more than willing to be a part of that. And we feel as though a lot of what we can provide in the video analytics and the situational awareness of what's happening on site, it's going to help out, the industry and operators in the industry as a whole. This is another one at a considerable distance away. Most of this one, I can tell by this would be very similar to what you'd probably have on a true install from a distance away. This is, you can tell I can see by this is one of the guys on the man lift, because you can see, you can almost look down on the top of the tank. We got as high as the wind and the comfortability of the man lift operator would want to go when we were out there. But this would be very similar. You're at a 60-meter distance with a autonomous leak detection solution mounted, looking down on a tank and looking for leaks of this size at a considerable distance. Yes.
It's a calibrated thermograph.
It is radiometrically calibrated as well. Yep. Yeah. So this is, and that's a good point, because this is a full-on. What is unique about this, and right now we're looking to solve the needs for the autonomous leak detection market, and that's where Providence solution is. There's potential chance for other integrators to be able to take what we're going to provide with Providence and say, hey, same time, this infrared camera can do a lot more. Do you want to do tank level gauging? There you go. There are integrators that could install that type of analytic for tank level gauging, same site, same camera. Maybe it's got a pan and tilt, and it's got a routine that it needs to look at things for a certain amount of time over an hour. But once an hour for 5 minutes, you can go look at the tanks and actually get a percentage of, tank level gauging isn't hard. A tank's this big, and I have this many pixels on a line. Well, this line I know is X amount of inches long, and I can tell you where that line changes temperature. Now, this is METEC. Keep in mind, this is just, I don't know if you've been to METEC before or heard of it. It's just like a Hollywood scene of that. It's not like true tanks full of product.
There's no liquid level.
There's no liquid level. I told them to put blankets on the inside, like heater blankets, but they didn't listen to me. Stretching out a little bit further, with this, same facility. Now we're looking at 80 meters distance for detection. Again, I believe most of these are between 60 and 90 liters per minute in size, if you want a reference of how big some of these leaks are. I believe most of the ones that we did at this 60 meter distance and beyond were really a considerable distance away. But in essence, you know, what you would see with this is where you kind of see the green and the palette color, just a red box or an analytic, because if it sees it in color, we just put a box around it, analyze it, send a previous, you know, a pre-leak, post-leak analysis video. Or, I mean, we'll have it with a UVMS system. So if you had this on 10 sites or 1,000 sites, just say, all right, site number 57, site number 4, or whatever you want to say, I can actually pull that up and pan and tilt, move that around, be able to analyze and see what's actually happening live on site. You know, the goal here is, you know, again, get the truck rolls off, get the truck rolls down, get it where people can go out there when there is a leak. A lot of technologies are out there. What we have heard from operators that have evaluated these technologies is that it's really challenging because it sends a leak and I don't know really what's happening. And I drive out there for 3 hours and it's a leak, or it was a vent, or it was, you know, there's nothing happening. It's can't find anything. So this is where the huge advantage of the OGI technology. I think I know what you're talking about. Talking about right here where it kind of blocks it out.
Yeah.
The other thing we're trying with this, it doesn't really matter. It sees it, but we are so right here where the window is, it sees that, but Providence is working with us on some quantification as well as analytic features, where when there's hard edge changes from hot to cold, a lot of times that's like the edge of a tank, where it's hot to cold, and that edge of the tank sometimes looks like a leak because it might be moving a little bit. So this camera's fixed on it, but wind might be moving a little bit. It may make it look like a leak. So they take a percentage of error on both sides, on the edge of that, inside and out, and say, all right, you can see that it's because this is a hot to cold edge here, hot to cold edge here. They take that percentage of error and they're buffering it. It still sees the leak, but it's kind of minimizing it just to make sure that it's not like the edge of a pole that's moving, because the edge of a pole moving could potentially look like a small leak. So they're taking those hot to cold edges out.
On the quantification side, it wouldn't show up, so it says it would be eliminated.
Correct, on the quantification side, but on this, it's still there. But yeah, it's quantification is also, yeah, looking from here to here, anywhere they see this, it's gonna pop up. And then this is gonna be, you know, just a different view, different angle. You can see, you know, right at the edge, you can actually, this one, you can see some of the red going around the edge, and that's going to be that analytic of it alarming in that red, when you would see that red, I don't know if you can see that kind of a little bit red edge of what's going on, and that red blob is what it would be showing as an analytic. And then, you know, when we start looking at this, you also have the capabilities to start talking about detection limits and what we're able, you know, to use this. And you can actually, and Yoshing talked a little bit this morning, essence of time. I don't have a whole lot of time to kind of get into what detection and the theory behind it, but you can set detection limit levels within the optical gas imaging technology to say, all right, what distance, you kind of go backwards with detection limits. You say, all right, what size leak do I want to have? And then I know the distance that I need to be and the delta T that I have. With this one, you can get the delta T because you can actually put you can put some sort of weather vane on there to get an ambient air temperature of some sort. So you can get the delta T pretty easily, and you know the distance. So now you can actually define your detection limit with a fixed mount solution of the technology, and to be able to understand exactly where your detection limit is given where this is and what conditions you're using the technology. This was one of the questions of what is the difference. There's a 1% contrast threshold on this. Not to get too far into this, it has to do with the noise equivalent temperature difference, what Yoshing talked about a little bit about, those of you that saw it this morning. NETD is a defined standard of how sensitive or how good an infrared camera is. If it's a higher NETD, we're going to need to understand. I believe Yoshing will have some testing plan right now to kind of test what's that maximum NETD for that 1% contrast threshold. on this. John had some discussion points on that. But what the Providence team has done is looked at, we have what's defined as noise equivalent concentration length, and they've defined kind of an NETD. And you were asking what is and the reason I put it, this is that threshold limit of uncooled versus cooled. If you're just focusing on the NETD, you're looking at a 33 to a 210. So, that's a, that type of difference. If you're looking at NECL, about 13 to 100, not too far off from either one of those. But the reason that I put this here is that there's different ways to look at it: NETD, NECL, noise equivalent concentration length, sensitivity standards on how to measure the quality of an optical gas imaging camera. This just kind of gives you that baseline of if we're looking at methane specifically, we have, it is around a 10x or so, 5 to 10x difference in pure methane as far as the uncooled technology and how it compares. Just so you know, we do have other cameras. Propane, I wouldn't even worry about propane for this. Is kind of just to show with the uncooled technology, you're not really I wouldn't even worry about the propane. It's so far up. But for ethylene, I don't know if there's anybody here, more for the ethylene, we do have a huge opportunity with the uncooled technology. If there's anybody interested in ethylene, the uncooled technology is a separate lens. So it's not going to see methane and propane together. Those would be two separate lenses. But we do have an ethylene solution that really almost puts the uncooled technology very similar into the cooled technology for a GF320 that's commonly used for ethylene detection.
On the eye test, when I saw that leak coming up, looked like a pneumatics next to a smaller vessel, not a smaller leak. Like the last one you showed.
Okay.
By the eye test compared to some of the leaks that I've generated on these grams, that looked like that could approach close to 60 grams. It's a smaller leak.
Yeah, it was. If it was 60 grams per hour of pure methane, we might be able to see it. But 60 grams per hour, half methane, half propane, is only, is a different story.
And that's same analogy. If you see, you can say down to three grams per hour methane, in that same quad away constituent, the methane part of that.
Yeah,
should be above 3 grams.
It just at the sensitivity, and it's also 10,000 parts per million.
That reaches that full concentration.
Correct, and that falls in. We could see 3 grams of 1 million parts per million methane, and so that does change the factor, change that factor a little bit as well. Yeah. And so so full on, a lot of different opportunities there. One thing you're saying is interesting. You said my eyeball. I've been doing this. You've been doing this for a long time in OGI. Is one thing that's good is as we start getting this analytic into cameras, evaluating, 2 things can happen. One, believe it or not, this little guy here is smarter than all of us combined. Computer can do things that our eyes and our brain and what we're able to do to look at a video, look at the screen of a camera, an eyepiece, to be able to detect leak. This guy right here is better at it than we are if we just teach it how. And that's what some of the stuff that the Providence team is doing in trying to ensure like we have the top of the line imaging solution for our analytic solution for optical gas imaging. In kind of in summary here, reality is we're taking the experience that Providence, Yoshing, and his team have in that analytic piece and utilizing and partnering with them, pre-official partnership, I guess you would say. We're taking that experience that they have and just pivoting over to what we see the industry focusing on in that methane detection technologies. Over that we've noticed for the last, realistically since the ARPA-E monitor project was where it really started in the U.S. specifically. So we're just taking that same technology and putting it in. But the issue is it's low bandwidth alarming, easily full scalable VMS. Again, you want to look at it, find it, pan and tilt it, go check it out. Low cost is a subjective term to some people. Lower cost than our cooled solution. But the more opportunities we have to get it out in the industry, the better chance that we can have a supply and demand drive our costs down. Where are we today? Yoshing and his team, they start, I believe, in 3 weeks or so, field trials in the U.S. to fully evaluate this. We don't want to just say we have a solution. Look, it worked in a lab. We want to take it out to an oil field and check it out for a couple of months to make sure it works appropriately and it meets the demands of our customers, and not just say it works, trust us. And so we want to make sure that we have the right solution and get feedback from people like yourself and operators out in the field. We can do this. This will be based not only on the uncooled solution, which is where we see a lot of the market asking for that methane-centric solution. We still have our cooled solution. So if this is of interest as a quad-away continuous fixed mount solution, we can use this with quad-away approved technology like a G300A and have a full continuous monitoring optical gas imaging cooled solution with the same analytic based solution that Providence and the team are working on. And again, the cooled midwave, higher cost, and we do have an opportunity for ethylene as well and some other gases to be able to use this. Kind of just an example, just an overflow of what this might look like with our pan and tilt. You'd have a power input box, maybe even an analytics platform driver in here. Everything else, you'd probably have an alarming interface to say, hey, something happened. And then you can have UVMS getting into your control room to either show the recorded video or potentially even go out there and install, and break in and actually pan and tilt it and go to the set point that it may have seen that leak, or the location that the camera was sitting, and say, all right, where is the leak and what we want to look at.
Is it not possible to have an uncooled midwave?
An uncooled midwave, there is such thing as an uncooled midwave. No, we have uncooled long wave. An uncooled high, I think that when you get to uncooled midwave, the thermal sensitivity of uncooled midwave is so bad it would be challenging to see a leak. And we could potentially make a 3.2 to 3.4 or CO2, something like that, but you really run into the quality of the imager being that, and the technology for uncooled, the materials that we're using, the sensitivity when you get to that level. There's a reason that they're all pulled up into that 8 micron, because midwave is even better. Like there's less water challenges with midwave, but you just don't have the image quality when you get to that. You probably wouldn't be able to see leaks at that point. Yes, sir.
Can you speak maybe to the maintenance? They're running.
It's a great point. So that is one of the down factors of the cooled system, right? So you've got a cooler that has to keep that, and that is a expensive part of that solution. We're working right now with our R&D group to try to streamline a fixed mount cooler to make it where it's going to run, bring that cooler, run longer, run longer and run more stable, and last considerably amount longer than where we have right now in our cool technology. The huge advantage of uncooled, you don't have to worry about that. This is you turn it on, and it's just plugged into the wall, just like, if you have a visual camera that does security right now at your house, you plug it in, as long as you got power to it, it just looks. Well, an uncooled camera from FLIR is going to be very similar to that. You'd have, whether it be a security camera in your, in your office or in your house or wherever you have, or whether it's an infrared camera that just happens to be filtered to see methane, that uncooled solution gives you that long-standing longevity. We have fixed mount systems, not OGI, but fixed mount infrared cameras that are long wave that have been mounted for 5+ years out in various industries for security. We've been doing this forever for security applications, right? You go look outside of a fence line for a refinery and you want to know when somebody walks close to the fence line, looks like they're going to jump the fence, and then you want the camera to follow them. That's what we do as a specialty in our security applications. And those have been out and mounted and running for a long time. Same thing with this. You're going to have that longevity with the uncooled. It's a huge advantage of the uncooled technology. Usually on average, you're going to need to look at if you're running it 24/7, the cooler is probably going to be around, generally probably around a 2-year, 18-month to 2-year span. And we're looking at trying to develop some unique technologies that expand that lifespan, that expand that tenure. If we can get it from 2 years to 3 years or whatever, that's a huge plus in our book. Well, I appreciate everybody's doing this, visiting with us. We'll have a booth out here. If y'all want to, and Providence will be right next to it. If y'all want to, and everybody's getting in this evening to set up. If y'all have any questions for us, please let us know. Let us know how we can help you out. Appreciate the time, and we'll be around to answer any questions. So thank you for your time sitting through the presentation today. Appreciate it.
Oh, do they automatically load it or do I do it?
Let's go.
You've probably done this several times.
File, open. What are you doing? Which one's you?
None of those.
Let's go to browse. One of those. Utilizing temporary control, safety. Is it one of these?
No, why is it? They put it in.
That I don't know. If it's not one of these, that's the only ones I know of.
So what do I do? Get my own computer?
If you have it on your thumb drive, I think you can run it in there. But I don't. Unfortunately, that's about the extent that I've
This
been.
is the right place, isn't it? It says it's in here.
If it was still 417A.
Well, did they change it? But on here,
Oh,
it's
maybe
here.
on a different computer. I see.
It's from here.
Where are you? Which one are you?
The following news, so 402.
Your high flow?
Yeah.
Okay. Yeah. That I can't help.
That's why I was interested to see what you guys are doing on there.
Yeah. And then, Mark, my colleague's going to be the one that is the moderator, and he'll introduce you guys.
Does he want to help us get the presentation up?
Yeah, if you have a thumb
No,
drive.
I don't have one on hand, but
Got one of my. That's.
I may have a couple of minutes here. I don't know if we're taking a quick break or not, but I wish I could help out.
no problem. I'm glad I asked you straight away, so I found the problem.
I actually, sorry I have to miss it. I have to run real quick.
Let me see if I can, Joe might have.
Yeah.
Thanks, guys. I gotta go. See you tonight or tomorrow morning. Okay, Mark, thanks. I will see you. Yeah. See you on the Zoom call soon. Yeah. Good. I've been chatting with helping to moderate, so I'm taking it over.
Okay, well,
However, I don't know what's needed from me, so.
so there you are. I have a presentation, but apparently it's not here. I did send it in, so do I need to move it or should I just fire it over from here?
Question. I don't know the answer, but I'm trying to figure it out, I guess.
Hello, I hear there's a problem. I'm here to call somebody to fix it.
That was good.
Your presentation?
Yes,
Yes.
yes.
Let me call Tucker and
You have it on your machine though?
Yeah,
Okay.
I mean, do you want me to just,
I mean,
USB? Yeah, we can just transfer it over if that's all right.
if you've got a USB, who's got a USB?
I don't know.
I might.
It depends on that PC.
I know.
We're a big company, but we're not allowed USBs.
I know, it's crazy.
Yeah, it'd probably take 3 days to scan it or something, you know.
Maybe like screen record, whatever. You don't have to do it. Let's go check.
Do you have one?
I'm gonna check.
What's funny is, Once you start having cow storage, you don't, I don't.
Oh, I know.
I don't use
I
them.
used to have 10 on me and
Switched to
yeah,
bags.
now my
So-
secret threatens me every day of the week.
I know I saw it yesterday, but I don't know.
When they came from being the best thing to being cursed at.
Can we use this?
Oh, I didn't. I'll say no. It'll do for a moment, and then we'll just move it over later. I can, well, I've just switched over on the PC side and that will do it.
Yep.
Okay.
That works?
It's stuck.
There's such left to do. That's okay.
Glad we could help.
You did a good job there.
That's all right.
I don't like taking blame, I'll take credit.
I'm surrounded by people like that.
Yeah.
I need you, you're in my inbox, I don't.
Man, I really thought I had it too. Hi, I'm Joe.
Spencer Series, our CEO, and David Booker is our CTO. To make the presentation.
We're gonna convince with him. Back on it, while I was up there.
Is the guys tonight knows what they're doing, give me a talk, right?
Who? I thought you, I just asked you, you got
Dude, I probably actually can.
You probably know more about this. You
As much information as y'all probably give out in the conversation. Something like this. Now, what you're.
Sorry.
And I was very familiar with the previous technology.
Okay.
4 or 5 years. I worked with Colorado State University to, with their spec.
On the open source project. That's gonna take the new, patent.
Those companies been making that product before even Colorado State came around, yeah.
So we're gonna get that.
So y'all going to the CH4 conference? Yeah.
Yeah, well, and they have this tap, exercise, they invited you to
Prior
to do the,
The only thing-
exposure.
I didn't see and couldn't get from you, Bill, is do you have a slipstream where you take a second for other slides?
Yes, yes.
I write repeat that, like, we're not typically, you must have questions. Say there's all CEO people, you know.
People don't really know.
Yeah.
All right, I'll leave you to.
Sorry, I thought you were on the bus there.
I didn't deny it.
Feel bad, when you talk for one late, they just bounce around.
So I'm looking at the time, seems to time to start. So, quick introduction from myself. I'm David Booker. I'm CTO of a company called Sensors, and we'll share a little bit of background. I'm joined with my 2 colleagues, Rob Wilson and Joe Morell. Rob Wilson's our VP of Marketing and Sales. Joe's our CEO. And we have a booth with this product on near the registration. Okay. So, pretty bold title, isn't it? Updated, improved high flow sampling device for fugitive methane emissions. Can I have a quick show of hands? Who's used the Bacharach high flow?
Use what?
The Bacharach, that's a good answer because that means you have. So there's at least 2 people who've used the Bacharach high flow. So I will probably just spend a few minutes talking about what high flow samplers are to make sure that we're all on the same wavelength. So essentially, quantification of fugitive methane emissions. We've all seen and been listening to OGIs today and other techniques for quantification, but we're now talking about a device that can quantify fugitive methane emissions with an accuracy of better than 5%. And you might say, well, what's the driver for that?
Are you on Teams on your?
I'm currently just using this as my computer. I can move it over onto this one at some stage.
Either that, or you could log on to Teams possibly, so that you could share the presentation on yours.
I've already uploaded it. You just don't know where it is.
Okay, I believe people are streaming with, that's what we got set up on this.
Oh, so
I don't have a thumb drive.
I won't interrupt you then anymore. You just keep going and I'll let them know what's going on back over here.
okay,
Okay.
okay. So let's just touch on some background of Sensors as a company. Founded nearly over 50 years ago out of Willow Run Labs in Michigan, with specialized knowledge on infrared detectors. And we've been working in this emissions industry for about 50 years, but not this specific industry, the automotive industry. So tailpipe sampling, measurement of regulated pollutants from vehicles. As a result of that, we've sold more than 400,000 4-5 gas analyzers. You're familiar with these for inspection and maintenance programs. So we know how to make measurements of gases from CO to CO2 to methane to total hydrocarbons, etc. And during that time, we've supplied these worldwide. So in the US, under the sort of auspices of the BAR program, but around the world in terms of other inspection and maintenance programs. Now, we're an employee-owned company, so we run an ESOP with over 80 employees, with offices in the US, headquartered just outside Ann Arbor in Michigan, but offices in Dusseldorf and Hong Kong, and of course mainland China, and distributors in other places around the world, including Korea and, as you can see, India, France, Brazil. So, ESOP company with a pedigree on emission measurement systems. Now, the nice thing about emission measurement systems, you all know that they exist. Everybody's heard about Dieselgate, where the issues with one particular car manufacturer perhaps not quite regulating the tailpipe emissions, got caught by our wonderful friends in the US EPA and California Air Resources Board and paid some pretty hefty fines. Now, what's happened as a result of that is that all vehicles being sold today actually have to pass an on-road test for emissions. Okay, so they don't just do it in the laboratory and check and put a tick in a box. We actually have to do real driving emissions. So that's changed our business substantially over the last few years for portable emission measurement systems. We also offer services. So we go out with our troops and we make these measurements for people. And we learn a lot about the products in doing that. And finally, we also supply OEM components, right? So we have integrators, for example, in the garage market, I don't know all the brands in the US, but companies like Snap-on and things like that would put our 4-5 gas analyzer into their module and package it and sell it into these markets. And one final leg of our business is on environmental analyzers. Okay. So you might say, well, why are we here? Okay, why are we wanting to enter space for fugitive methane emissions? For two reasons. We became aware that the de facto technique for quantification of methane using a high flow sampler, that product was withdrawn from the marketplace 4 or 5 years ago. We're also aware that that product is now obsolete and difficult to service. And yet there is a need in the industry to make such measurements. And in order to make those measurements, we need to measure methane and we need to measure flows. We can do both of those associated with what we've learned associated with our automotive activities. So this is the equipment that we put on the back of a vehicle, okay? Doesn't it make it beautiful, isn't it? Right, reassuringly expensive equipment on the back. that's used essentially to check the emissions of vehicles. And we're measuring while we drive, or the manufacturers are driving these vehicles and demonstrating compliance against the regulations, carbon monoxide, carbon dioxide, nitrogen oxides, THCs, non-methane hydrocarbons, particulates, the whole gamut of regulatory pollutants. And you know that this is a regulated market. So it's really important that we have the accuracy and the traceability. So if I said that that was a fugitive methane emission measurement system, it really nearly already is, because it can measure flow. So if I put a vacuum and pull in the leak, measure the methane, I can calculate the leak rate. So this is our pedigree, and this is why we entered. So I would like to just share a few slides on some background on what we decided to do and why we decided to do it. So we didn't get a big show of hands on people that had used the Baccarat high vol sampler. We got another one now, okay? And this is a product that was put out there over 20 years ago. And as you can see in the picture here, they would extract with excess flow the leak out of a particular component, in this case using a bag, that they would measure the total flow rate and the concentration with gas measurement technology in the rucksack or backpack and calculate the mass or volumetric leak rate. And you can see here, they claimed that they could measure leaks up to about 10 CFM. And they could do that with an accuracy which was claimed around 5%. Now, most people who've used the Baccarat say, well, maybe that 5% is pushing the technology. But we decided, well, if we're going to enter into this space, we've got the benefit that electronics and technology has moved on over the last 20 years. So we want to increase the flow rate, perhaps up to 30 to 50 CFM, and the leak rate correspondingly up, but also validate our leak detection at 5%. And what I'll be doing and showing you in this presentation is where we are in terms of this product development as a replacement product. So this is our minimum viable product. Because we're new into this market space, we've been, and in particular the three of us, have been engaging in lots of conversations. We need people to tell us, are we doing it right? Is the packaging correct? Are we actually hitting the right target in terms of the usability and the need for such a product? But it's not quite a copy of what we've got. So the project that I led within Sensors in a team of engineering was a minimum viable product. So we're not wanting to finish absolutely everything. We want market feedback on this product at this stage. It started late last year and completed in July this year. And it was about the need to sort of get early adopters, to optimize the specification and get stakeholder feedback. Now, at the same time as us doing this, we're also aware that Colorado State University was running an open source program funded by the California Air Resources Board for a replacement device to the Baccarat. And this project, again, started on a similar timeline as this. And at the moment, they've produced a prototype device that is similar to the Baccarat device, using off-the-shelf parts that you get in Home Depot, I think, that literally is there for quantification. And because the objective with CARB was to attract other people to start to manufacture such a device, they've slightly changed their track. And in September, we have been invited to go to CSU to actually perform some measurements at their METEC facility. So we'll be demonstrating this product in Colorado in September. So what is the design of this product? And this is where we kind of had to just make some decisions. And we've been asking people things. The Baccarat device, as you see, is a rucksack device, tube that you count. We said, well, hang on. If we can measure methane, maybe tomorrow somebody else is going to want to measure some other toxic. Maybe we want to measure some other pollutant. Do you have a side stream coming off that I can go to another gas analyzer? So we decided we'd split this high vol sampler into two principal components. And the first one was I call it a gas sensor battery and control electronics module. You can tell I don't work for the marketing department, but it's very much an engineering sort of description of what it does. So in this electronics module, we're going to house a range of gas sensing technologies. We're going to have the battery pack so that we can run it for a day in the field. And we're going to run, in our case, a single board computer with a modern architecture in terms of Wi-Fi. Because we're envisaging this product being operated with a tablet PC or a phone or something like that. The second part, which is connected by an umbilical cord, will be the handheld unit, which essentially would, and excuse my language, will suck up the leak. Okay, it will suck up the leak by excess flow with all the methane coming into this handheld unit. That total flow rate will get measured, and a sample of that flow rate will be taken by an umbilical cord all the way back to the gas measurement for the concentration measurement. So as long as we know the concentration measurement and the total flow, we can calculate the leak rate of the methane. And the procedure that you operate to prove that you captured the whole leak is you vary the flow rate. So you may do 2 or 3 measurements over a 1 minute period. I don't know, how long does it normally take you to do a back-of-rack leak measurement?
2 or 3 minutes.
1 or 2 minutes. So you might operate at 1 or 2 different flow rates to check that you've captured the whole leak. And there's an SOP in place, and even Colorado State University published an SOP for the use case for these sort of measurement, which we'll be using as our basis. So if we now take this sort of module, I have to caveat it, okay? And I caveat it and say, we built this thing, you can see it, we've got several of these units, and we can do all the metrology, but until we've engaged stakeholders and got feedback on the use of it in the field, we're a bit reluctant to go through all the ATEX certifications, which is a long and expensive process, until phase 2 of the project. So the unit we've got, and you'll see on our booth, isn't ATEX approved. So we will go and do some very simple measurements, get customer feedback, and then we are already in the process of launching phase 2 of the project, which will be final engineering and safety certification. And we've been told it must be class 1 Div 1 approved in order to have wide acceptability. Everybody who wants to have a play with it can get some small exceptions, but for general use, class 1 Div 1 is what we've been told. So what does it look like? It looks like something that you would find in as a gardening tool in terms of a leaf blower, as you can see. But in this case, it's a vacuum system. And you can see on in the metal box, that's our gas and control module, which we can mount on the base plate, on a rucksack. Now, we've been told that the first thing that the person who's going to do is going to take this into the field, it's going to put it on the floor. And they're going to attach a 2-inch or nominal hose to take the sample. Well, this can easily just be put on the floor. Those units can be separated by a long umbilical cord. So you may, for example, use the handheld unit to suck up the leak in the particular geometry you're dealing with, and have a long extension lightweight cord back to the gas module to measure the concentrations. So very flexible from that point of view. So if we look at the 2 parts separately, you can see what we've done in this unit. And so in this particular box here, we are running metal hydride lithium-ion battery pack to keep the weight down. I'm going to show you what we're doing on gas sensor technology, but I'm not going to show you everything about what we're doing on gas sensor technology. But we'll show you the metrology. And in our case, we want to measure from a handful of ppms all the way up to 100%. And the rest of it is fairly straightforward and obvious as an instrument box. But in terms of flexibility of this design, we can, of course, take a sample from this to another bag if you want to do speciations, toxic work, or even change and look at different analyzers within the actual device. The handheld unit is really the main part of the unit, because we have to have a blower. And the blower configuration we've got at the moment will operate up to about 30 to 50 CFM. And I keep 30 to 50 CFM because, as you can imagine, if I operate it with very little restriction on the inlet, I can get up to 50 CFM. If I start restricting it with long sample lines, that flow rate will come down a little bit. It's quite lightweight with about 7 pounds in terms of weight. And essentially, we've also played with the concept that you can control the whole test using the on-off buttons, the sort of way you would operate a sort of handheld unit. So very simple 48-volt ATEX fan. So gas measurements are the key as well, right? We as a company make gas sensors. We've been doing this for 50 years. And I show you here one of our benches. It's an NDIR bench that we make. I also, out of interest, have also included the STX sensor, which was used or recommended by Colorado State University. But we're also looking at using TDLs. So we want to make this model. I always use the phrase, and they always laugh at me, and I say, we'll make it reassuringly expensive, right? Actually, we want to make it reassuringly reliable and accurate. And we think this is going to be at the price where you would expect a product like this in terms of the backrack type pricing model, a device like this. So if I show you the metrology, this is what we actually got. Okay, I'm a scientist. I never plot linearities on a log-log scale, because if you plot them on a log-log scale, you can get rid of anything. I mean, you can show anything on a log-log scale. But the reason I have to show it on a log-log scale is because I want to demonstrate that we are measuring concentrations over 5 orders of magnitude. So in this case, we can go below 10 ppm all the way up to 100%. And what I show you here is 3 gas bottles. So we're doing a 10-step linearity just with 3 gas bottles, blue, orange, and the grey, and the 10 corresponding 10 steps, just to show you the performance of these devices. And obviously it looks linear, but that's log-log. So I have to show you that we can't really show you on a log-log. I need to show you the error by percentage by point. So the next chart I show has the same, has the same log x-axis, but I'm now showing you the measurement error by percentage by point. So that would be the reading minus the reference divided by the reference. So this is absolute 2%. You can see all the dots are within an uncertainty error surface of 2%. So if I can measure gas concentrations over these wide range within 2% of accuracy, with traceability back to international standards or NIST, I have the basis of an accurate quantification device. But that's one part of the story, because this is already extremely useful. And that is, we've now got to measure the flow. Okay, so we're going to measure the flow. And we as a company have over 20 years experience in making flow meters that measure exhaust flow on vehicles. And you can imagine the challenges of measuring the exhaust flow on a small engine or a heavy truck or whatever with the same sort of accuracy criteria. And they require errors which are typically in the 1 to 2% range over the dynamic range, with temperatures going up to 600 degrees C. So we have this technology, and we're going to use an averaging pitot. People know what an averaging pitot is. Industry uses them for flow measurements. But we're doing a lot of mathematics on top of that in order to make sure that we get this dynamic specification and useful specification. So to illustrate the challenges of what we have with an averaging pitot is we make it bidirectional. I give you the illustration with this simple scavenging engine at the bottom, that we've got reverse flow. So when you start putting a fan close to a pitot, we all know in the gas industry that causes pressure pulsations, it challenges for accurate flow measurement. So because we have this ability to measure at high speed and accurate flows, we can actually measure our flows with an accuracy of better than 2%. So now we've got 2% and 2%, and we could pretty much do the basic sort of error surface and say we should easily be able to meet 5% in terms of metrology. And I say that from a theoretical point of view. I'm waiting to go to METEC to validate that, because it's one thing me saying that I can measure it and we can do some of all the parts. The other one is in the practical application, am I actually going to meet that full 5%? So flow measurements, we as a company have spent a lot of money just on infrastructure for flow calibration. This is not something you can just make in your garage. in your basement. So we have a full traceable 17025 type calibration infrastructure for flow measurements, because flow is really important for what we're doing. And when we use our device and apply the device all the way back to the handheld unit, this is some of the early data I've got on our flow meter. And what you can see on the bottom, I've got the reference flow in CFM and the measured flow on the y-axis. And you can see I'm going from around 50 CFM all the way back to around 10 CFM. And I'm showing you in the orange dots the error by percentage by point. And again, we want to be within about 2%. Now, people who are fluid mechanics and the chemical engineers in the audience know that, you know, we can improve that. I mentioned that I haven't, in this data, didn't have a Reynolds number correction to the discharge coefficient to extrapolate down into the few CFM sort of flow range. And when you put these flow meters together, how robust are they? Because this is the other thing. We want it reassuringly robust. We want this to work in the field year after year after year. And we've been working closely with the European Commission on error surfaces of flow meters. And we demonstrated that over 5 to 7 years, providing that you don't drive over the flow meter with your truck and change its geometry, they are stable and don't deteriorate. I mean, essentially, they are nothing more than a mechanical flow device with a pitot and pressure sensors, which are easy to calibrate. And when we look at that and look at multiple flow tubes, you can see that we can keep repeatability, standard errors, intercepts, slopes within 1% from a whole variety of devices. So this is really encouraging for us in terms of the metrology of what we've got in this unit. So we've got accurate gas measurements, we've got accurate flow measurements, and we've got a sort of integrated package that should, we believe, and this is where we really want the feedback, meet industry's requirements for this accurate quantification when you decide to do the quantification using a high-vol sampler for that accuracy and climate governance type drivers. And my final slide to conclude is really this, that we've completed phase 1. You can see the equipment on the booth. We are going to METEC in September to do some testing. We are also talking with a number of people that are here in this conference to do some market testing of the device. And phase 2 has initiated in terms of the final engineering design and the certifications. So at that point, I really would like to thank you for your attention from the 3 of us and open the floor for any questions.
When you talked about VLC down to the ppm level, for small leaks, we can get a very, well, from experience, we can have capture at lower flow, say probably 30 feet. So I noticed as you went down to 10 on the graph, we had very higher positive error.
Okay, yeah.
So I was wondering, is this going to be good? How is it going to get low as a lower concentration?
So, okay, that's really good because we believe we're going to implement the full algorithms that we developed for the flow meter. In this case, we didn't, because at the time we were told saying you only need a 2-3 times turn down ratio on your PWM controlled fan. So I said, well, okay, we'll run from 50 down to 20. Okay. In fact, there's clear advantage to be able to run down to 5. We've got good turbulence. We have no problem. We've just put a discharge coefficient in to flatten that orange curve.
And truth be told, just being a CEO, I asked him the exact same question a couple days
ago. So to give you,
ready for it.
But to put it into perspective, on turn down ratio of a device and flow measurements, in the automotive market, where it's all very, very much regulated by the wonderful EPA that regulates by litigation, and we know how they'd love to do that, they really want defendability, and so do our customers. We have to operate with engines that have a turn down ratio from idle to wide open throttle that are 30 to 50 times. So we can get 30, in principle, we could get 30 to 50. So you could go from 50 to 1 and still meet your accuracy criteria.
Do you have, and I can't do it in my head, but do you have an idea of what you, based on what you just said, lower flow, lower concentration than we saw before. Before we had around so many grams per hour.
Yeah.
Lower temperature. You have an idea what you think you might, I don't know.
No, I
Where
haven't.
you think you can get, how low can you go?
I don't know. I really don't know. The question's a really good question because when we've done the error surfaces, because it comes back to one of the good, how low can you go? How low do you go before the background methane becomes a dominating error surface? Now, I know when I talk to friends some of the people we've met, they say to me, look, the background is silly, right? We're not going to measure a leak where the leak's at a background level, right? Or perhaps not, it's so low, we need to detect it. So they don't do background corrections. But how low can you go? I think it will be governed by the background methane level in the
How low would
facility.
you want to go?
Well, with what's going on in the world and some of the pneumatics in California, I mean, what you report is your lower limit of detection for something.
So for example,
So the lower you build is the lower you report on an annual basis for reporting.
so it's law of diminishing returns as well, because if we go down sub ppm in terms of metrology, background methane is going to become a big influence on this whole process of excessive dilution. So 5 orders of magnitude, I would expect at least 4 orders of magnitude from the upper leak to the lower leak.
Taking that back to that Elmore days, we're doing the emission estimates. When we did all the new studies, do those, we typically got an order of magnitude or 2. And that's when you start moving decimal places, it's a big deal for reporting aspects.
Yeah.
So it seems to be you're moving the decimal places.
I hope so. I hope so.
Sometimes more than 2, it looks like possibly.
Okay. Yeah. But yeah, I mean, if you compare this principal specification of error surfaces by point and concentrations over 4 orders of magnitude, keeping within 2%, that just is, and it's not just, it's also interferences. So we're using a combination of gas measurement technologies to mitigate any interferences, right? So we also know the backlight device, the sensors in there had interferences. Those interferences were again clouded this overall accuracy of the device. So we're using combination of TDL technology as well as NDIR. And part of that is interesting because I'd like to think that at some stage we may even be doing VOCs. I can imagine these are quite important at some point, and people want to know that from an interference point of view. But METEC is meant to be doing this in September. They've published and shared a test program that they're going to complete in 3 weeks of testing in September that includes a variety of leak rates as well as interferences. So, to be interesting.
Your anticipated or expected price point?
I think you'll find that if I speak that way, they'll go, you can't say. But I'm not going to tell you, I'm not going to tell you, we're thinking this is going to be around the $40,000 mark. Is that fair, Rob?
It's something 35.
Yeah. And that's similar to what the background price would be if you're adding 20 years of inflation. It's, or as I say, a third of the price of an optical OGI camera.
Yeah, I think the goals of the METEC study were lighter, cheaper, and a little bit more dynamic range.
So I always play and always laugh at when I use this reassuring, because there's always this threat that this need could get scrutinized under a regulatory framework. Metrology is really important. The cost, the working capital involved in putting one of these into the field it's trivial compared with the labor cost. And what is even worse is if you have a failure, you know, if your equipment failures. So robustness, metrology and accuracy, metrology, I think are more important than just whether or not you can shave out a few $1,000s in the cost of such a product.
Yeah, if you gotta spend 40,000 on a feedback too. That's crazy.
It's and I don't think, well, I guess the other thing is, are you shooting for just methane or VOCs?
At the moment, we're characterizing the system. It will measure predominantly methane, that's our focus, but we're looking at interference gases. And in areas where we get overlap on our gas measurement technology, we should be able to get some semi-qualitative VOC data out. I mean, for example, it's possible we could even be looking at some sort of surrogate THC.
Because the sensors on the back right were finding it kind of bad for us because of the crossover issue.
Yeah.
I mean, that could be solved with software.
Yeah.
And some smart people, but.
But even if you got just methane, with a port, okay, if we need to go VOC, we could use what everybody has is a TVA to get a concentration, because you have a certifiable flows
Yeah.
that we could do
So
to use anything.
out of this handheld, exactly, out of this handheld, we've got a well-mixed diluted flow that we need to make the concentration measurement. It goes down an umbilical cord to that gas module. It goes in and comes out that gas module. You could attach a bag.
It's not destructive to the IR, right?
Yeah. So you could put whatever, you could put a bag and do bag sampling. You could do method 21. You could do a whole range of things downstream.
To allow to method 18.
Yeah.
To back to study going.
Yeah. So this is where we are, and obviously what the three of us are really looking for is feedback, encouragement. We are and have started, pre-orders, of course, yeah. So, any other questions? If that's it, we'd certainly like to thank you for your attention, and come and join us at the stand and have a look at it and handle it and give us your feedback. So
I saw it looked like a leaf blower, but do you have attachments or something?
Yes.
To make it flexible?
yeah, so the idea is, I mean, that's the first thing is the go-to sampling arrangement is a bag with a 2-inch hose that you will attach. So we will have a range of adapters for doing this bag sampling. We are interested in doing some work with an OGI also to show that this extra vacuum, if you like, the 30 to 50 CFM, may mean that some leaks you don't even need to bag. We've got that much extra flow. But we don't know, we've got to validate that.
But that's some of the stuff that we are hoping to get from your community. As we hope to join your community, that's not our expertise. So you need a flexible tube, how long does that tube need to be, what's the diameter, what's the end condition of it. That's not our bailiwick, but we're willing to listen and go do.
Well,
Yeah, it is.
the tools we've had are what we live with. A plunger, going over it.
Yeah.
When we do these, we don't bag every component. We put it over it. We hopefully have enough with the other one. We had enough velocity, and with the camera, you check the other certain things you do to make sure you got capture of no VOCs coming out. So usually with that higher flow and the way the component was, we had capture. You could prove capture by viewing it to the camera. And lower flows, you probably get better capture at lower flow rates.
Yeah.
Such as we're talking about getting lower.
Right.
Yeah.
So it's just, we just bring upside down plungers, a lot of times what we use.
We're not always looking up to the tailpipe of the car. We got lots of different shapes and sizes.
Yeah, it could be a big.
It's not a one size fits all.
We didn't have a lot of shape. We had that shape, but we have a lot of sizes. So, yeah, but the input would be phenomenal, because that's the piece that we have to add to it. That wouldn't be available.
And the heat exchanger has challenge. I've melted equipment,
I've taken 5-gallon buckets, turned it upside down, drilled a hole in it, put a water bottle up to the top, tape that to it. Put some slits in the bottom of the 5-gallon bucket, put it on top of the ship, where we're estimating emissions off a panel on the ship. And, we have the vapors coming in through the little sawtooth sparks on the 5-gallon bucket. And that hose goes right to the top of a water bottle. So there's a lot of times we make things out.
yours looks like a leaf blower, sometimes leaf bags, so you're your favorite friend.
Yeah.
The bigger, the plastic. And duct tape.
They got this recognized.
Okay, well, thank you.
Thank you. Actually, we fixed portable aerial.
Over there, or you go to something nice.
I'm gonna go to the stand, I think.
Oh, that
Next
was,
one, I want to attend.
It
was.
There, that's specific.
This, this.
And it's one.
LNS,
just.
big protection.
One.
Whole intersection. Heath?
He wasn't here. He was supposed to be here.
But yeah, get 3 people. Mike. And Paul.
Yeah.
That one.
Yeah, so, I mean, most of their standards, but it works. I can compress this, you know, is, we got it. That's green, right? They don't.
I didn't know they were streaming this.
No.
Had we known that, we would have, I would have bought a damn thunder. I have one, because I switched bags.
But it's really interesting because they've not told us anything. We uploaded it, said it's uploaded, and I think because the chance for numerals, it was in a different.
I asked them about that too. That confused the people in the front, the registration desk.
Damn good, thanks.
I literally just got in.
Oh, have you? Oh, you've got to work straight away.
Are you Paul?
No, I'm Milton.
I'm Joe.
Joe.
So we,
Meet you.
Yeah, good to see you again.
Yeah, I'm sorry. I
Rob just headed over to the booth just to see if people are up here. Take a look at it. They have it on display.
You just got in. Be over. Oh, yeah. I had the kids this week. My wife has been out of town, so I got 4 kids, and so trying to do the office thing and keep them in line.
Where's your home on?
I'm in Missouri, Texas.
Okay.
So Houston.
Okay.
You?
Back in Ann Arbor.
Oh, you're all, yeah, that makes sense. Okay.
I'm not always free to.
yeah.
My old stomping ground.
Yeah.
They tell you, yeah.
Oh, we've had that discussion.
Yeah, no, it's been done.
I'm
Yeah.
trying to decide which one of you is bigger U of M fan. You or Rob.
I have to come to your office and see.
You come during September, you're gonna catch a game.
So he says, right. I did actually get to go to the golf course. You said you guys are set up on the golf course, if I'm not mistaken, typically.
He is.
He is, okay.
You say you guys.
Okay.
He is.
That's-
Sometimes he invites us, sometimes he doesn't.
Okay.
Yeah, it's literally, he's got a nice.
Well, I'm
real
sure
nice setup.
his tickets are limited, so probably the party scene is a little bit more like open.
I mean, more people stay on the party scene anyway. Last time I went to his little tailgate, and this, you can see the front gates of the tailgate. We just stayed there all day. Damn, we catch that on TV.
I was a little kid when I first started going out to games there, and we started out in the golf course, so I have very fond memories of doing that.
Did you grow up there or here?
Nope, I grew up in Massachusetts, so there were enough trips that added up. And very memorable. But when I became a student, though, it was wow to be right in the middle of it. It's great. So,
My youngest is in grade school and she goes to school with our boys.
oh, get out!
Yeah, so I see him every day.
How? You said what grade or age?
She's going into fifth.
Oh, they got some young ones.
He's got really young ones too. He's got a second round.
Yeah, I guess that makes sense. I got one in the 5th grade, 4th grade. Yeah. I need to keep up 5 kids.
He's got one that's 2 years old, 1.5 years old. Yeah.
How many kids total?
So he's got in this marriage, I think 4, and then previous marriage is 5.
Oh,
4.
okay.
Yeah.
That's hard to keep up with. Who's is there a moderator here?
He pops in every once in a while.
Otherwise you are.
To moderate, I
Oh.
don't want to give any of the instructions.
Okay. All
But
right.
we've got a technical IT team that, yeah, he's struggling back there.
So we weren't on the list, you know, list of presentation, is that the?
And so, who else we got in here?
Think so.
You base that. And, I saw you in the elevator. What's your name? Say again. Anna, nice to meet you.
Thank you. Yeah, we infrared detection,
You do what?
infrared detection.
Okay. Base out of.
We're in Jersey.
Really?
Yeah, I have clues infrared.
You are, you know, Kevin.
Oh, yeah.
How you doing?
Yeah, doing well.
Good seeing you. Wow. Yeah.
That was weird.
Oh, yeah. Gee, would you that one?
Yeah.
Fast, furious.
That's all relative, so like, remember.
Oh, okay, yeah.
Wrong side.
He's coming here on Friday.
I see, so that's type of,
Okay.
now I'm part of Telegram, so, yes, that's easy. Yeah, yes.
Okay. Yeah, Paul's not gonna be here till Thursday night late. He's got this FEMSA thing, right? Yeah. So you said New Jersey, and I understand things are pretty harsh over there as far as COVID with lockdowns.
Yeah.
Yeah, the guy who's supposed to be here, Mickey, couldn't travel for
Oh, really?
that reason.
Oh, wow.
Yeah, so I got stuck with the presentation.
Look at you.
Yeah. But I was counting on him to come in here and do it. I had no idea they had a full day going on today outside of just training too. I thought it was like exclusive training because I'm not training. This is not training, right? Yeah.
But if I get you going on Teams,
Oh, okay. Yeah, we're already up. I just pulled it.
have you logged on to Teams?
Oh,
No, yeah, let me get that going. It'll just take a second.
Sure.
Here.
Oh, you're doing live?
Yes. This one was actually from the one earlier because the gentleman before me